That's not good. That's better. Yes.
All right, so thank you for the invitation. First of all, this will be a quick communication, so I have 10 minutes. Let's go. This is not actually exactly joint work with Eric and all of these good people, so Steve and Luis. This is an argument that came up during a work with them in persistence theory and how to apply homological algebra to that. So this is like a little part of it. It applies to other contexts, and this is why I talked to you about it today. So this will be in a combinatorial fashion, I guess. And let's go. So 3 steps: we ask a question, we give the answer, and we have a strategy to answer it. This is the question. So what is the global dimension of the endomorphism ring of spread modules over a finite grid? I have 4 terms there. The first 2 should be fairly familiar to all of you. The other 2 I will take the time to define. So if people read the slides afterwards, because they are not necessarily all aware of all these things, global dimension, it's the longest you might need to take projective resolutions. And the morphism ring is if you take a module, consider all the morphisms from M to itself. And it turns out that this is an algebra. Oftentimes you will take a module over an algebra and then consider the algebra of the endomorphism ring. And this makes it so you can study other algebras to learn something about one other algebra. One typical approach is in tilting theory, where you start by taking sums of indecomposable modules, for instance, all the projectives, in that case, it's the algebra itself, and then you take out summands and replace them with new ones. Our approach is slightly different. It's an approach that's used elsewhere as well. So instead of replacing them, we just keep adding more and more indecomposable summands. So our algebra is the incidence algebra of finite grids. So you take, here for example, it's the 5 by 3 grid, but you could take any grid size you might want. So you would want all the commutativity relations there if you want to start from simply a quiver. We will always orient things from bottom left to top right, as so. And these are well known to be of wild type, meaning that understanding all the indecomposables is pretty much hopeless. So what you want to do is take approximations. The first type of approximation you might think about is projective approximations, but these are way too weak. They just care about the dimension vector. They don't care about the maps between your spaces. So what we do is we will approximate with the larger families of indecomposable modules. In our case, it turns out that the thin indecomposables in the 2-dimensional grid are characterized by their support only. And this is pretty nice, and it allows us to make everything work with drawings instead of technical modules. So this is a grid. So it's pretty large, but this is still a finite grid. Now, if we take a module and it's thin, it needs to have this staircase shape, or else the commutativity relations won't hold. And what I was saying that they are determined by the support is that if the maps, instead of ones, we have other numbers in there, then it's still isomorphic to that one. The argument is not super hard to follow, but I won't go into the details this time around. And let's just note that if we go into higher dimensional grids or arbitrary postsets, this is not true anymore. But in our setup, it works. So this means that the only thing that matters here is the pink box. So let's remove everything else. These are the objects that we will talk about today. So if we have 2 boxes, so the green and the pink one, we can have morphisms from one box to another, so from one module to another. And like in type AN, the morphisms will go backwards, so from pink to green. For instance, we could put 1s in there, and everything else is forced to be 0 because either the domain or the codomain is 0. And this would be a morphism, but the other way around, there won't be a morphism. So from green to pink, there won't be a morphism. So what's the answer to our question now? If we take the sum of every spread module, so the module as I just described, and provided that the grid, if we take n to be the height, so we have a height, and the length is long enough compared to the height. So basically, we can take this up to infinity, it's fine. So if the difference between the height and the length is big enough, then the global dimension of the endomorphism ring over all these spread modules that we can see visually is twice the height, so twice the minimum. I'll talk about the generalization if I have the time in the end, but essentially we can go to higher dimensional grid and it still works. So there's two steps to this argument. First, we show that if we fix the height and increase the length as much as we want, after a certain point, it cannot grow any longer. So that point is 3m plus 2. Actually, it's smaller than that, but the argument is simple for 3m plus 2. And the second step is to compute what happens before it stops growing. So let's start by understanding what the Gabriel quiver of the endomorphism ring looks like. So the vertices are given by the sum ends of the module over which you take the endomorphism ring. And the arrows are simply the relative irreducible morphisms. So we want to understand what the irreducible morphisms, well, the relative irreducible morphisms look like in there. So if we were to take every single module, this means that the Gabriel quiver of the endomorphism ring would be exactly the Sander-Wrighton quiver. But in our case, it's like removing vertices in there and arrows. So starting with a spread, I will use a sort of color scheme to talk about morphisms. So we have a morphism from pink to blue there because we add a box behind. And instead of having confusing lines like this, I will use this notation. So I have the pink spread, and I have the blue box. This means the morphism from pink to blue, where you add the blue box. You can also go the other way and remove stuff from the end. So if you remove that corner, you map still from pink to red, but now the notation will be remove the red box. Now, maybe it looked irreducible there because you only remove one discrete step. So what could be in between, right? But it's very similar to string algebras where it factors through adding more stuff when in certain situations. So here, if I did not have the bottom square there, I could factor through that one. So it wouldn't be irreducible. So it's irreducible only when your connected component, when you remove the box, goes all the way to infinity. If it's connected, then the single connected component is fine and it's irreducible. But in the cases where removing a target of your set disconnects the set, then it needs to verify that condition that the side that you remove goes all the way to the boundary. And in the same situation, but dually, if you add those boxes, these are three different morphisms, right? The middle one is already irreducible, but if you had, say, the top left one, you could also add the box above it first and then remove it because now it's a target, right? Because we are on the edge. So these are actually the irreducible. The morphisms that I just showed were not irreducible. But now we do have all the irreducibles. So yeah, you can describe them combinatorially. What you want now is a way to extend grids. So we define extending functors and in the opposite direction, snapping functors, hence the title. So let's go over them again in drawings. So if I have the 3x2 grid on the left side, I can embed it in many ways on the right side, and the functor will be simply copying every space for each space in the block. So for instance, the first 4 blocks here would all be the same space at 1, 1 if I choose a given modules. And every map between blocks will be the same map. So for instance, here we can see it explicitly. So we have identity over an entire block, and every map from the 1, 1 block to the 1, 2 block is just F1, 1, 1, 2, F1, 1, 1, 2. And dually, you can extend this to an actual adjoint, an actual functor, but you can also just define it as a function on the spread modules, not over the entire module category. And in that way, it's easier and more combinatorial to define. So when the box is empty on the right, you bring it back to an empty box on the left. And when there's something, even if it's not the entire box, you bring something. So hopefully this is a clear description of how it works. So these two, well, now function and functor, but you can extend to a functor. Have the following property. So morphisms from arbitrary spread to a module that's an extension are the same thing as a morphism from the snapping of your spread over the smaller grid to the module before you were extending it. Using a couple more arguments, which I don't have the time to go into details, you can show the following, which is essentially the main tool that we have for the answer that I talked about. Essentially, it says that if you respect all the all the domain of irreducible maps coming into a module. Projective resolution in the endomorphism ring over the small grid are sent to projective resolution over the endomorphism ring of all spread modules over the large grid by the extension functor. It's not, so essentially we follow this path. I don't have much time, so sadly we will go over it. So it's not all embedding that works out. For example, this embedding is not good because if I take an irreducible on the left, it does not map to an irreducible on the right by the extending functor. So you need some other thing. For instance, this embedding will work out. And this is where the 3M comes in. So we will need the entire column for every source and for every target, because you can these define what your spread is. But you also need the column before every source, because you can add them in irreducible morphisms. So that's 3M. So there can be a single source or spread on every row, and you need every column where there is a source of spread, so 3M. And the +2, I don't have time to talk about it, but essentially you want the 1, 1 or the 0, 0. You want the first and last column to stay in there. So keep them +3M, 3M +2. And now all that leaves us to talk about is, well, okay, we at some point will stabilize. What is the dimension before that? So all that we, it turns out that the depth of a resolution is actually determined by the number of irreducible that comes into a module. For instance, if we take this spread, we can add 1, 2, 3 box before, and we can remove 3 box at the end. So it would look something like this. If we do every operation, we end up on the right side. And all these operations, because the spread is generic enough, are commutative. So we get something that is Boolean. This would actually be exactly the top of a projective resolution of the endomorphism of the simple at that spread in the endomorphism ring. Now, maybe these operations are not independent, but in most cases, it's still commutative. For instance, here maybe a top left box disappears and reappears, but it's not a problem. It's still Boolean. But there's one case where it's still a problem, and it's that one where if you remove a box, it's irreducible to project on each disconnected component, right? So you could remove the right strip or the entire row, and this means you have 2 ways to remove a box. That messes up everything, but these are all extensions of the 4x4 grid. So once you have the global dimension for the 4x4 grid, you take all the problems and throw them away. And this means that we are done, because you have twice the number of sources, and that's the end of the proof. Let me just mention that we can extend this to arbitrary dimension grids. It looks a bit more complicated, but it really isn't. It's just that the M and N here, you don't select one, you select which one to remove. So it's the product of everything, so N by M, and then you remove one of them. Now, product of everything, remove one of them, take the minimum and cross those, and that's it, that's your result. And I went over time, but yeah, thank you. If you have questions, don't hesitate.
Yeah, questions? Does this give us a bound on the global dimension anamorphism algebra of a sum of spread modules that's not all of them, or
no? No, not at all. Because when you take when you add or remove things in your endomorphism ring, you can mess up the irreducibility. So it's not strictly increasing, it's not strictly decreasing, can go both ways. So adding more stuff can make global dimension grow, can make global dimension go lower.
do you have any idea of what the overall bound, or if you took any possible sum of spread modules in those dimensions, do you have a sense of what the upper bound on that?
There is no upper bound. We can easily get something that is infinite, even with a finite grid, if you select spread modules and reject other spread module in a strategic way. Yeah.
Can you say a bit about how these grids arise in persistence theory?
Yeah. Essentially, in the one-dimensional persistence, you have a filtration of space, and then you apply homology, then bam, you have a representation of AN. So if you have multiple parameters, then you have two ways to go around, and then you take homology, and then you have a two-dimensional representation. Of course, it's a continuous step, but you can have, well, if you start with finite data, then you have finitely many steps, and then you can extract from this a finite grid. Yeah.
Thanks.
No problem.
Any other questions? Okay, well, that's thanks, Peter.
Thank you.
And let's see, it's coffee time.